This video is about the pyramid of stability. The pyramid is used to determine all the possible oxidation numbers for any given element. It's going to be used to tie your understanding of oxidation numbers to your understanding of sublevels. Remember when we talked about the Bohr diagrams? These rings, the electron rings, are actually composed of sublevels, the S, P, D, and F. That's what we're talking about when I show half full and full sublevels. NSA means no special arrangement. Half full means you have one S electron, or 3p electrons, or 5d, or 7f. If you have a full sublevel, you have 2 s electrons, 10 d's, or 14 f's. Notice there is no p electron discussed in full sublevels. That's because if you have a full sublevel, or 6p electrons, you actually have a full octet. When elements participate in bonding, they're trying to become more stable, so they'll give or take electrons to increase stability. If that gain or loss increases stability, you'll be moving down in the pyramid. Any exchange that improves stability creates an oxidation number. If the exchange does not improve stability, it is not an oxidation number. If you're using the pyramid of stability and you find that you have an electron arrangement that's not one of these that I've written down, it's not a half full sublevel, or a full sublevel, or a full octet, that means that you have a no special arrangement situation. This is the least stable of all of the electron arrangements. The other thing that you need to know is that we will be focusing on the electrons found in the valence electron energy level, and we're looking only at the S and P sublevels. There are elements that use D electrons and F electrons to improve their stability, but we won't be using the pyramid for those. Okay, so let's do some examples. I have iron, which is a metal. Its default is a +2, so that means it has 1, 2 s electrons. Nitrogen, nonmetal, its default is -3, 1, 2 s electrons, 1, 2, 3 p electrons, total of 5 electrons, which means we have a negative oxidation number. Arsenic is in the metalloid section, which means that it can be a metal or a nonmetal, which means that we have to run arsenic through the pyramid of stability twice, once as a metal and once as a nonmetal. It also has a default of -3, so we have the same electron configuration as we have for nitrogen. So we'll start with iron. Iron is a metal. All metals give electrons. We have 2 s's, which means we are already at a full sublevel. We're going to give electrons away one by one until we get to a full octet. How do you do that when you only have 2 electrons? Well, remember, this is the valence ring. When you give away those 2 electrons, you reveal the ring that's underneath it. That ring always has a full octet. You can't have a valence ring unless the ring below it is full. So we'll give away 1. That means we now have 1s. Well, we've gone from a full sublevel to a half sublevel. That's not more stable, because remember, stable is down, so we're actually less stable than before, which means that this is not an oxidation number. We'll give away our second electron. All of the s's are gone, which means basically the entire valence ring is gone, and the ring underneath it has been exposed. That ring is a full octet. That's as stable as you can get. we've given away a total of 2 electrons, so our oxidation number is +2. Our next example is nitrogen. Nitrogen is a nonmetal. Nonmetals take electrons. So we currently have 2 S's and 1, 2, 3 E electrons. So that's where we're going to start. So we're here at half full. Remember, we're going to take. So we're going to add 1. So 3p becomes 4p's. 4p's is actually less stable. It's up here under NSA, not an oxidation number. Add another. Now we have 5p, still NSA. Add another. We now have 6p electrons. We're here at a full octet, as stable as you can possibly be. Total number of electrons taken, 1, 2, 3. Oxidation number, -3. Okay, now we're going to do arsenic. Now remember, I told you arsenic was a metalloid, so we're going to have to run it through the pyramid twice. Once as a metal, once as a nonmetal. So we have 2s and 3p electrons. Remember, metals give electrons. So 3p, we're up here at half full. We're going to give 1. 3p becomes 2. Let me scoot this up a little so we can see. Not any better. We're back up here at NSA. 2p's become 1. Still no improvement. Give all of this away. We now have 2 S's, which is a full sublevel, so we've actually improved. Total number given so far, 1, 2, 3. So our first oxidation number is +3. Continuing on, we're here at 2s. We're going to give 1 away. 1s. We've gone from here, we've gone up to half, not an improvement. Give away all the S's. So again, the valence electron ring is gone. We've exposed the ring underneath. That gives us a full octet, perfectly balanced. 1, 2, 3, 4, 5 electrons given total. Our second oxidation number is +5. Now we're going to do the same thing as we did with the nitrogen with the second part of arsenic. So again, we're at 2s, 3p. We're going to take 1. 3p becomes 4p. And as before, we went from half full to NSA, not good. We're going to take another 5p. Still no improvement, still NSA. 6p. Back down to full octet. We've taken 1, 2, 3. Our last oxidation number, -3. So our oxidation numbers for arsenic are +3, -3, and +5. Our next example will be tellurium. I've chosen another one of the metalloids because it gives us a chance to do this for both metals and nonmetals. 1, 2, 2 S's, 1, 2, 3, 4, 4 P's. 4p puts us at NSA. Metals give. We're going to give 1 away. 3p, which takes us to half full. So our first oxidation number, +1. Give away another 2p. Now we're up to NSA, so we don't want to use that. Give away another. Same thing, we're still here at NSA. Give away our last P. We're now down here to 2S, full sublevel, so we've improved. 1, 2, 3, 4, given away total, second oxidation number, 4. 2S, give away 1, becomes 1S. Give away the last one, everything in that outer valence electron ring is gone. We're now down to the full octet. Total given away, 1, 2, 3, 4, 5, 6. So we have +1, +4, and +6 so far. Non-metal, 4P, NSA. Take 1, becomes 5P, no improvement. Take a last one, 6P, we're down to a full octet. We have taken 1, 2, -2. So our 4 oxidation numbers for tellurium, +1, +4, +6, and -2. My last example is tin. I've put it here because this one gives troubles to a lot of students. It's in the +4, -4 column. And a lot of students believe if an element is in that column, it's both a metal and a non-metal. That's true for some of the elements, but not all. Tin is considered a metal, so the non-metal version doesn't exist. So when we run this through the pyramid, we're only going to do the metal part. 2S, 2P, we're here at NSA. Give away 1, 1P, no improvement. Give away the second P, we are now here at a full sublevel. 1, 2 given away, +2. Give away another one, 1S. We're going to go from the full backward to the half full, not an improvement. Give away the last one. Again, all of the electrons in the outer ring are gone. You now have a full octet. 1, 2, 3, 4. So our oxidation numbers for tin are +2 and +4. That's all you need to know using the pyramid of stability.